This week's lecture is on chemical equilibrium. It's going to be nice as we only have one chapter this week, and it's going to be short and sweet. All right, so when we look at dynamic equilibrium, this is the rate of the forward reaction being equal to the rate of the reverse reaction. A reversible reaction is a chemical reaction in which the reverse reaction contributes significantly to the overall. As you can see in this example below, the two reaction rates are at the same equilibrium. The extent of the reaction in dynamic equilibrium can occur at any point in a reaction. As we can see in the bottom left-hand picture, we have more reactants with product. The equilibrium is shifted to the left. On the right-hand side, we see that there's more product and less reactant, so the equilibrium is shifted to the right. Let's consider the following situations. Which sentence describes each possibility? Which one of the ones on the left has equilibrium to the left, and which one has equilibrium in the middle? Well, when we look at these 5 different examples, the equilibrium lies to the left in example A. You can see there's a lot of, at the start of the reaction, at equilibrium we still have a lot of A. In example C, we have about half of the reaction at equilibrium, so it lies in the middle. The concentrations affect these reaction rates. The higher the concentration, the faster the reaction rate. So with the reactants going in a forward manner to products, the rate of the reaction is equal to the concentration of the reactants to the order. So down here we see the reactants and the forward products. It is fast rate at the start. We've got a moderate forward rate as the reaction proceeds, and it begins to slow down as the reactants are consumed. The same can be said about reverse reactions. As the forward reaction occurs, the concentration of the products increases, which speeds up the reverse reaction. But in dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction, as we can see in this example. Next, we're going to look at the equilibrium constant, or KEQ. On your quiz and exam, midterm exam, you're going to have to be familiar with this because you're going to have one to solve. This states where the equilibrium of a reaction lies at a given temperature. So this is going to be a multi-step type of, this is an example for a multi-step reaction. You can see we have A plus B going to C plus D. Okay, so we got 2 reactants and 2 products. In order to figure out KEQ, we put the products over the reactants and we multiply them. Here's one part that I want you to be really familiar with. If you have a 2 in front of one of your reactants, you have to put that as though you're squaring it in the problem. So a big 2 in the front becomes squared down in the bottom. Here's an example. If we had 2SO2 plus O2 going to 2SO3, you can see we have the 2SO3 here on top, and the 2 ended up squaring the concentration. We then divide by the SO2. You can see over here there's another 2. We have to square that one. Okay, so keep that in mind. That's very important. So if we write the equilibrium constant equation for this reaction, it would be as follows. You can see again we've got the 4 in front of the hydrogen. That ends up being down here. So we raise it to the 4th power. And don't worry, I do have an example coming. All right, so if we, I'm going to skip that last one, but the following chemical reaction has reached equilibrium. Okay, 2NO plus O2 goes to 2NO2. We're going to calculate the equilibrium constant if the concentrations of the reactants and products are as follows. All you have to do is fill it in. Okay, so on the top we got the reactants, right? Or the, so 9.32 times 10 to the negative 6 squared. Okay, because remember we got the 2 in front. And then we've got the, for the NO, there's a 2 in front as well, so we have to square that one. So we're given the concentration. All I'm doing is filling it in, products over reactants. The second reactant, okay, we have to multiply it, is 2.28 times 10 to the negative third. That's for oxygen. We don't have a 2 in front of the oxygen, so we don't square it. Here's where I want you guys to be really careful. Practice putting this in your calculator. All calculators work a little bit differently. What I do, and sometimes it takes a little bit more work, is I turn these into an actual number. So I take 9.32 and I turn it to like 0.000000932 and I square it. I use that as for my calculator. My calculator does not like it when I put these powers in there. If you can figure it out on yours, more power to you. But when you plug all of this in, you should get 2.4 times 10 to the 12th. And you are going to have an example just like this on your quiz and exam. So understanding this, if the KEQ is greater than 1,000 or 1.0 times 10 to the third, that means that it favors the products. If it's less than 1,000, it favors the reactants. So here's another example of what that might look like. So KEQ, okay, less than 10 to the negative third is far to the left. Between 10 to the negative third and 10 to the third, it's pretty equal. And greater than 10 to the third, which is greater than 1,000, it's far to the right. Next is Le Chatelier's principle. Be familiar with this term. If you disturb a reaction at equilibrium, the reaction returns to equilibrium by shifting in such a direction as to partially undo the disturbance. So if the initial equilibrium has an equal forward and reverse rate, and remove all of the SO2 and O2, okay, which are part of the reaction here, the forward rate will become 0 and the reverse rate will become disturbed. The rates will become equal again as time passes. So if you added SO3 to a vessel in which the reaction was 2SO2 plus O2 going to 2SO3, at equilibrium, which way would the reaction shift? The reaction would shift to the left, creating more SO2 and O2, and would remove the SO3 because we increased the concentration. Temperature also has an effect on our reactions. Reactants plus, or going to products plus heat, is referred to as an exothermic reaction. We have the energy of the reaction being negative. Heat plus reactants going to products is an endothermic reaction. The change of the energy reaction is positive. Let's consider the following exothermic reaction. Removing heat by cooling would shift the reaction equilibrium to the right. So we remove heat from the exothermic reaction, removing it, as you can see here. The reaction is going to shift to the right and generate replacement heat. If we heat an exothermic reaction, it would shift to the left. So here's a question. If you placed an endothermic reaction in a freezer, would the equilibrium shift to the left or shift to the right? As you can see, we're adding heat. Since you're removing heat, the equilibrium would shift to the left. Here's something you may be familiar with. My 7-year-old absolutely loves this heat-changing putty. It's called Think Putty, and when she plays with it, it's normally purple or pink, and then when she plays with it, it turns purple, I think, or vice versa. This changes color when the equilibrium reaction that changes position with a change in temperature. The reactants and products are different colors, with the exact colors depending on the substances in the exothermic or endothermic reaction. When the putty is held in your hand, the temperature is raised from 70 to 99. Such a temperature change is large enough to shift the equilibrium from one side of the reaction, which is one color, to the other side, which is the second color. Next, we'll look at solubility. You're going to need to know the definition of solubility. Solubility equilibria defines the amount of an insoluble material that dissolves. As you can see here, we have iron sulfide. At equilibrium, the ions dissolve and precipitate at the same rate, with the result of the concentrations of the dissolved ions being constant. The solubility product, or KSP, is refers to sparingly soluble salts with the KEQ. So KEQ equals the solubility product, or the concentration of iron times the concentration of the sulfur. So here's what I need you to know. The sample KSP values, this shows their solubility at 25 degrees. Okay, we have all of the numbers next to it. I would never expect you to memorize these, but I do need you to know which ones would be more soluble than others based on their KSP. So here's an example. Of these salts all listed here, what would be the most soluble in water? Meaning that you could mix it in and it would, dissolve. Okay, so looking at all these. The answer is magnesium carbonate. It's got the lowest KSP value of 4.0 times 10 to the 5th. So that means it's the most soluble. So going back to this list, okay, you can see here, that makes it the most soluble. So with this, make sure you understand the definition of solubility. I don't expect you to know great details about it, but know that it's the definition is the concentration of the substance in a saturated solution. I also want you to be able to determine which one would be the most soluble based on a list of KSP values.